Our penultimate speaker of the day is Peter Goddard, who will tell us how to solve the scattering equations.
Well, I'll follow tradition sincerely and thank the organisers for putting together this meeting. It's a pleasure to be back in Cambridge. I'm going to, as it's been said, my title is Solving the Scattering Equations. I guess partly I'm trying to explain why you wouldn't want to do this, but I will in the process, in order to understand that, explain how you do it. The work I'm describing here is based on directly on work that I've done with Louise Dolan, and it follows the work of byCachazo and Song He and Yuan, of course, and then earlier work of byFairlie and David Roberts, which I'll refer to, and also connects with work of Grossand Mende. And then more recently, in the last few months, there's a bit more work that will come into what's here. And then there are many other related interesting papers by numerous people, some of them here, which connected with this, but I won't list them all. Let me begin by giving a general overview of the talk, then say what subjects I might cover given time, and then start on the main subject. So what we're going to be talking about here always are a system of n massless particles, and I'm not going to consider loop diagrams. You can discuss those, as we've discussed extensively this morning in some way, and Louise and I have worked on that, but that's not going to be the subject of my talk here. I'm going to talk about things which relate to tree amplitudes. But the basic setting is that for n massless particles satisfying momentum conservation. So in other words, it's this setup here. Each of the k squareds is 0, and there's some number of them indexed by A, set A, and they sum to 0. And the scattering equations, which are the subject of this discussion, are these n equations, where n is the number of elements of A, which are actually not order independent. There are n equations in n variables, but there's a Möbius invariance which relates them. And so that means that you can, if you like, fix 3 of the z's, be anything you like, in 3 distinct points on the Riemann sphere, and that then leaves you, in effect, with n minus 3 variables, and there are 3 relations between the equations, so you get n minus 3 equations in n minus 3 variables. And it was found early on by observation and perturbative analysis that there are typically n minus 3 factorial solutions. Part of this discussion here is how you can understand that. And the particular line that we've developed is to look at these equations and to write them in an equivalent form which is polynomial in the z's. Now, of course, if you have a set of equations like this, you can clearly, by multiplying by products of the differences of the z's, put it into a polynomial form. But the polynomial form that you would get just by crudely multiplying up would not be at all efficient. Everything would have degree n minus 1, I suspect, and that would not give you any understanding of what was going on, really. So the fact is that they are equivalent to a rather neat set of equations. Actually, I think it's rather very, very pretty. And those equations, there's one. If you specialize 3 of the z's at 0, 1, and infinity, then you'll find that there's one of these of each degree from 1 through n minus 3, and they can be written down very neatly. Written down there, you consider subsets of all the particles, and you consider the total momentum of that subset, which subset S, Ks, and the corresponding products of the variable z. And then what you do is you take the square of the total momentum for the subset and multiply it by the product and sum over subsets of a certain size. And so that gives you n minus 3 possibilities, because if you took in that equation there the size to be 1 or n minus 1 by the conservation of momentum and the fact that the particles are massless, you'd get 0. So those are the things you can write down in that way. N minus 3 of them, and the equations, the scattering equations, are equivalent to those equations. So there after you fixed, after you fixed 3 of the z's, there are n minus 3 equations, n minus 3 variables, and the degree suggests from the standard theorem in algebra that the typical number of solutions will be the product of the degrees, which in this case is n minus 3 factorial, since there's one of each degree. And in fact, we can prove that assuming that all of the ks squareds are non-zero, that there is always exactly that number of solutions. So the additional feature that we have here is that these expressions, these equations, are actually linear in each of the z's individually. So their degree is 1 through n minus 3, but they're square free. That is, the z squared never occurs. So that's a very special feature. And so we have 2 special features. One is that we have one equation of each degree, 1 through n minus 3. And the other feature, these features have different effects, is that each of these equations is linear in any one of the variables taken separately. The first thing tells you how many solutions there are, n minus 3 factorial, and the second one makes it much easier to solve. So there are standard procedures for attempting to solve these sorts of equations, which quickly get out of hand if you have too many equations or too high degree, which actually started in Cambridge in the middle of the 19th century by Cayley and Sylvester. So a whole development of trying once they realized there were methods of eliminating variables between polynomial equations and not just linear ones, a whole subject developed, and that subject in the end, after it became sort of conceptualized, gave birth, I guess, to algebraic geometry and commutative algebra. And along the way, in trying to solve these equations, people developed this solution, both Cayley and then subsequently Macaulay, another Cambridge person, though he spent his life as a school teacher actually. They introduced concepts, eventually the basic concepts of commutative algebra, ideal theory, and so on, and then they forgot why they were doing the problem, at least from our point of view. That is, these beautiful subjects developed, but if you try to go to the books and find an explicit formula for solutions, you'll be somewhat disappointed. There is a more recent work by Gelfand and others, a book which tries to relate the sort of explicit formulae to the more modern developments, but it's actually quite difficult to read. At least I find it difficult to read. Now, the other thing that I should point out is that the coefficients that occur in these equations are familiar from any development of particle physics. They're exactly the Mandelstam variables, and so they're the invariants associated with all the possible channels that you could find, and so they're very natural things to occur here. Actually, sadly, Mandelstam died earlier this week. So the general objective then is to consider the remarkable expressions that CHY found as for the amplitudes of massless theories, a whole range of massless theories, as integrals of rational functions over these z variables with the integrands concentrated at the solutions of the equations by, say, putting the equations in the denominator and taking integrals around poles. So that when you do that, the solutions, the end result is necessarily a sum over of a rational function evaluated at the solution of this set of equations whose coefficients are themselves rational. That is, at least in terms of the basic coefficients we're taking, which are these Mandelstam invariants. And it then follows by results in Galois theory, which again I think you'll find quite tricky to track down in exactly the right degree of generality in the books, but nonetheless they're true. That the end result of all that has to be a rational function, and we know that rather remarkably these things are rational functions. So all of that is somewhat of a deterrent from actually solving the equations, because if you solve the equations and you go past n equals 5, you're going to introduce irrational expressions, if you can get expressions at all. And of course, once you get up to past n equals 5, you get onto sextics and so on. So you're lacking exact expressions in terms of roots and so on, if you were foolish enough to try to do it that way. And at the end of the day, you're wanting all this to cancel and to get back to the original stuff. Now, you know that there are lots of formulae, Newtonian formulae and so on, for the expressions for sums of symmetric functions and so on over roots, and you could try to express everything in terms of that. But fundamentally, what one is doing is saying that associated with this set of equations, or regarding this set of equations as a set defining some sort of zero-dimensional space, a zero-dimensional variety, termed as scattering variety, in terms of this, the definition of this zero-dimensional variety, we can associate some algebraic geometric object to this variety, which is the scattering amplitude. And the rest of it is just some way of pretending to calculate it. And so the objective, the general objective, not always in the near headlights of this sort of approach, is to try to understand that what natural geometric object this is associated with this scattering variety. So, but the thing we can emphasize is that these scattering equations, the scattering variety if you like, encode the kinematics of a collection of massless particles satisfying momentum conservation. So somehow, and the particular solutions to these equations, which are complex, of course, and as I said, given by expressions you can't even necessarily write down, are really not of interest in themselves. And they don't, it's different. It's not that you think anything physical in some sense happens there, if thinking them as associated with the world sheet of a string or something like that. This is just a set of equations, just a geometric object which leads you to something that you're interested in. And the fundamental question of how or why all this works, I think, is still mysterious to me. And so that's part of what we're trying to do here, is to try to understand more about that, or to understand something about that. And for me to do that, I think that the answer to that question there's nothing in this setup so far which has mentioned anything other than scalar field theory. You don't have to add on adjoint representations of anything, or Yang-Mills, or gravity, or whatever. Now, it might be, of course, that, as was being suggested perhaps this morning, that by one or two questioners, that to understand it, you need to be intrinsically in the context of supergravity. If that were true, it would be an absolutely remarkable statement for me. I mean, that is that here you've got something which says that these things encode massless theories, and to understand this, you have to invent supergravity. That may be true, but if so, I think it would be an extremely deep statement. So for the moment, I'm just trying to understand it without that, and to understand everything just in terms of the simplest possible theory. So this is what I might cover in the talk. I talk about the scattering equations and their Möbius invariants, talk about the tree amplitudes and a bit about where this came from. And a fair bit of this has been covered already in the morning, so I can perhaps go faster than I otherwise would go. Or alternatively, you can console yourself with the fact that repetition is the soul of pedagogy. And then I'll say a bit more, prove the polynomial form for the scattering equations, talk about how you solve those equations in various cases, and then, and in general actually, and then perhaps talk about what's particular about four-dimensional space-time, and how all of this relates to ideas about Möbius transformations and other equations that you might write down which are somewhat like this. And in other words, trying to understand this and trying to put it in a slightly bigger mathematical context which produces other equations. Okay, so we have these equations which I've already explained, and they're invariant under Möbius transformations. That's birational transformations of the z's, and because of that, essentially they don't determine they can't determine the nz's. They can only determine the orbits under the Möbius group, and so the n equations must have must have three relations between them, and you can make all of that explicit. So after after we've fixed 3 points, and most of the time I'll be fixing z1 at infinity and zn at 0, and sometimes z at z2 at 1. But if you fix z1 at infinity and zn at 0, you've knocked the number of variables down to n minus 2, and you then have a set of projectively projectively invariant equations. That is, each of these equations has a particular degree still, and that's quite convenient to think of this variety as everything here is being doing in the context of projective geometry. So if you want to quickly see the Möbius invariance of the equations, you can just check it out. It's not difficult, but it's easy if you use this which is a function familiar because it's the essence of the integrand of bosonic string theory, tree level. And normally in that context, you're looking at situations where k squared is 2, say, but here we've got it equal to 0, and normally what's Möbius invariant is not this, but this times the measure, and here it's just Möbius invariant by itself. That's why when you do the integration, you have to put in what's referred to as the Park-Taylor factor that was there earlier. So this is actually invariant under those transformations, provided that k squared is 0 and that the sum of the k's is 0. And that's very easy to check. And then it follows from that the expressions which give you the scattering equations have to be Möbius invariant, because the things that we put equal to 0 is just a logarithmic derivative with respect to one of the variables of u. And if u is invariant under Möbius transformations, then although its logarithmic derivatives here will be covariant, if they vanish at one point, they vanish at the Möbius images of that point. So this is, if you think it through, it's very easy to see that implies the Möbius variance of the system of equations, and it also tells you, by considering the infinitesimal invariances of u, it tells you what the three relations are. So CHY gave us expressions, and they, by the way, initially framed everything in terms of gauge theories and gravity, but then realized, as we did, that it works for scalar theories. And I'm mainly talking in terms of scalar theories. So, but for the theories that they considered, you have this expression, which is essentially what you need for scalar theories, together with some other part of the integrand, and you heard about that this morning. It has forms that you can specify for Yang-Mills and for gravity, but for phi cube theory, it's just 1. And then, writing down these expressions, you'd like to have a nice argument to say that this does actually produce the tree diagrams of gauge theory. And when Louise and I started looking at that, that's what we were trying to do. We knew that Shirk had proved in the zero slope limit that that you got out of out of the original Veneziano model phi cube theory, and out of then out of the more elaborate models that you then got Yang-Mills theory and so on. And this was a technique which was much employed to generate field theories of interest. But what's going on here, which is, as we see, is connected, and it was implicit in the work of Grossand Mende, is really not to do with that limit, but the other limit. And that's been talked about this morning, and I still think there's well, we don't understand why it is that somehow in what looks to be the alpha prime goes to infinity limit, we get out the same thing as we get out in the alpha prime goes to 0 limit. And so when we eventually proved this, we had to resort to using a BCFW approach, and in that way prove at least for phi cubed and Yang-Mills, and no doubt it works for the others, but we didn't have the energy to do that. But it's rigorously true that this produces the tree amplitudes of the field theory. Okay, so it's already been covered in this morning's lectures, exactly how you write these down for the various theories, so I won't dwell on that. And also a benefit this morning that somebody went to derive the 4-point amplitude, but let me just mention that again. So in the case of the 4-point amplitude, if we specialized Z1 to infinity, Z2 to 0, Z4 to Z1 to infinity, Z2 to 1, and Z4 to 0, then, and let's call the other variable Z, an enormous problem saying Z and not Z. But I would feel awfully unpatriotic if I said Z. So if you do that, then and you choose to look at F3 as the independent one of the scattering equations, then you get this integral, and you can evaluate this integral simply by taking the residue at a pole, and you get the answer that you should get. So that's practically how you do it. You can do this with a two-dimensional complex integral using appropriately. It's a bit more complicated. You have to be aware of how you handle integrals of functions of more than one complex variable around singularities and so on. But it's all straightforward in the end once you got that reasonably under control, and you can work things out there. But and you by contour deformation, you don't have to face looking at the actual solutions of the equations. And that's basically the sort of technique we use to prove it in general. So let me just say a bit about where this comes from. And for that purpose, just write down some of the notation of string theory. So in string theory, the variable which describes the sort of complex version of the position of the string is this variable x of z, which is dependent on the sort of mean position of the string and the momentum of the string, and then these excitation modes of the string, and which will be our harmonic oscillators on quantization. And there's a sort of momentum type variable obtained by differentiating this. And what you find, that what corresponds to the reparameterization invariance of the string, if you start from a Lagrangian point of view, or you find holds true with suitable intercept if you just start from the amplitudes, is that p squared vanishes in terms of its expectation value on a state. And that's essentially the Virasoro conditions, and it's that enables you to get a theory which doesn't have negative norm, as long as you're in a dimension which doesn't exceed 26. And of course, the spectrum you'll find, although is much more complicated if you're less than 26, and for that purpose, you want to be in the critical dimension. But that is not necessary for anything we're talking about here, and I'm a bit suspicious of where it occurs elsewhere in these sorts of discussions of things with a finite number of particles. So this was actually, these equations were first written down by Fairlie and Roberts in 1972. And what they were trying to do, so that's 4 years after Valenciano wrote down the first theory, and by that time in 1972, people were trying to see how they could get more general string theories. They could get lots of, well, they weren't string theories at the time. That was not until the several months later that people realized fully the equivalence with string theory. But there was an effort to try to get things which would not have tachyons and not have ghosts. And it was already perceived that there were tensions here, and although you could write down theories in which you could push those problems off to probably arbitrary high energy levels, they seemed to be there in the end, unless you were in these very special situations in which you had tachyons and in the end were in a critical dimension. And so they were just looking around for some other approach, and they hit on the idea, Robert's thesis in the end, of writing down instead something without the oscillators in, but with singularities. Instead of having just one logarithmic singularity which is at the sort of source of this momentum, they put in a number of them, but they put in no oscillators. And then to mimic this, they put down the condition that p squared should vanish identically. So here it is actually constant, but that constant is of order h bar, so it goes to 0 in the classical limit. So they wrote down this, and these conditions here, as we'll see, are exactly the scattering equations. The condition that this vanish for all values of z. So why is that? Well, it's because giving out. Oh, there it is. So if we look at this expression, it's got a most double poles, and it won't have any double poles if when you put a equals b, the numerator, which is ka squared in that case, vanishes. So let's assume that, so it has no double poles, and then let's write down a condition that it has no single poles. Well, the single poles might be at ZA, and the residue of the pole at ZA is just this expression here. And if that vanishes, then there's no, if that vanishes for a given A, then there is no pole at Z equals ZA. And so then this thing has no poles. On the other hand, it goes down, clearly it goes down at infinity, like 1 over Z squared. And then de Neuville's theorem tells you it vanishes. So the vanishing of this sort of this light Virasoro condition is exactly equivalent to telling you actually that telling you that this is a system describing massless particles satisfying the scattering equations. And so then some years later, I guess 15 years later, the equations came up again completely independently, and in fact I'm not sure that Grossand Mende ever realized that Fairlie and Roberts had got them before. When they were considering the condition, they were wanted to analyze the high energy behavior string theory. And so they looked at the integrand, which is basically this, of the expressions, and for the amplitudes, and they wrote down the condition that the phase should be stationary. And so this leads you to the idea that the fact that it should be stationary is that this derivative should vanish. And that is exactly the form of the equations that we had before. And so there, the z's satisfying this do have an interpretation at the points at which the phase is stationary. But this is to do with the high energy limit, which is the opposite of the low energy limit, which is the one in which the zero slope limit is appropriate. And that mismatch between the two limits, I think, is still a mystery, at least for me. So now I want to prove, proof relates very much to what I've just said, that the polynomial form for the scattering equations. And so what I've done on that slide is just write out what I told you earlier, that these equations are equivalent to these polynomials, and in a given polynomial you sum over all the subsets of a given size, and so you sum over n factorial over m factorial minus n over times n minus m factorial. So we've already said that the scattering equations are equivalent to the vanishing of this Fairlie-Roberts quantity p squared. It's vanishing for all values of z. And so it will vanish precisely if when we multiply it by we clear essentially all the denominators out if that quantity vanishes. So if we multiply by z minus zc producted over all c, then we will indeed get something which is polynomial in z, and then the coefficient of each power of z must vanish if that's going to vanish identically. And so you can just calculate what that coefficient is, and you see here what you get if you look at a given power of z. You get a power of it is multiplied by a product of z's of the complementary number in n minus 2, and because this is all of degree n minus 2, and then that product is multiplied by a sum of ka dot kb's over a and b not being in the product, and so that then gets you an expression like this, where actually this is the k squared for the complementary set, but k squared for the complementary set is the same as k for the set by momentum conservation. So it falls out like that, which of course was not the first way we found it, but it's obvious once you see it. So as I say, I think they're rather natural and rather pretty set of equations. So in that analysis there, I hadn't fixed any of the z's, but now I want to fix one at 0, which is easy. It just disappears from the sum, and one at infinity. Now to fix one at infinity, I'd better divide by it and take the limit as that one tends to infinity. And that just picks out all of the terms in here in which the product involved z1, and all the ones in which it didn't just fall away. And I then get an expression which now, before these things had degree 2 through n minus 2, and now it's 1 through n minus 3. And so now you get the sum of k squared over all the subsets of a given size, but they have to include k1. So we still, after we've taken that limit, we still have to feature these are homogeneous expressions. They're defining a projective variety. We haven't fixed any of them at 1, which we could if we wished. And they're still linear, of course, in each of the z's. And so now, typically, they determine the solutions, and typically they're equal to the product of degrees, which is n minus 3 factorial. And as I say, you can actually prove it's exactly that, as long as those Mandelstam variables don't vanish. And you can, of course, you can take the previous expressions, which Freddie et al. Gave us, and rewrite it in terms of these polynomial constraints, and of course you expect to get a fairly neat answer, which you do. So that's explicitly just converts over, but there's no great gain in that. The gain is in writing down a set of more manageable equations. So what about the solution to these equations? Well, we've already really, in some sense, looked at n equals 4. If you look at n equals 4, then the two subsets of 1, 2, and 3, which involve 1 or 1, 2, and 1, 3, and so you get, and there's just one equation because there's n minus 3 equations, and so you get this equation which we essentially already solved before, and then the solution, if you put it into that integral, will give you the answer. When you look at the next level, next value of n equals 5, then you have a linear equation and a quadratic equation. The quadratic equation is square-free, of course, as these things always are. But if we eliminate x between these two equations, which is a sort of straightforward thing to do, then you get an equation which starts involving squares. So as soon as you start eliminating things, the thing is no longer square-free. And what you get then is something quadratic with two roots. The two roots happen to be equal if the 5 momenta lie in a 3 space. So now typically the 5 momenta will lie in a 4 space. We're now in arbitrary large dimension in general because Freddie gave us these things for any dimension. And so if you take 5 momenta, which that is number 5 of momenta, then and they add to 0, then typically they're going to live in a 4-dimensional space. If they happen to live in a 3-dimensional space, then the roots of these equations coincide. And you might hope that result generalizes higher up, but unfortunately it doesn't. So we don't have any neat geometric interpretation of when these roots, which are determining the points, coincide. So we know we have n minus 3 factorial points, but some of them might be coincident, and you have to count them according to their multiplicity, as always with algebraic equations. So if you write it out on this slide, then it's easy to see what's happening. If I call the variance little a, b, c, and big a, b, c, then eliminating x gives me this quadratic, and I could get at that quadratic a different way, which I'm going to show you now, just because it generalizes higher up. So if I can write this quadratic in this form, and the reason I can do that, if I look at this expression here, so this is h1 and h2, this is the linear expression, this is the quadratic expression, and this is the derivative of those two things respectively with respect to x. So if I write down this expression here, it clearly vanishes on the solution set, because if both h1 and h2 vanish, that determinant vanishes. On the other hand, it's clearly independent of x, because if I differentiate with respect to x, the derivative of the first column is 0, because x only occurs most linearly in anything. And the derivative of the second column is the first column. So that expression there, and this is trivial in this case, but that expression there is both vanishing on the solution set. If you look at it, it's clearly quadratic in y and z, and it doesn't depend on x. And so it must be that quadratic that we've written down there. Well, that gives you a way of dealing with higher cases. If you look at the next case, then n equals 6, then we have 4 variables. After we put one at infinity and one at 0, and we have a linear equation, a quadratic equation, and a cubic equation, and the product of 1, 2, and 3 is 6. So this is going to give a sextic for z over u, say. And you can check again that this sextic is given by this expression here. So here the suffixes, it's a bit perverse, but the superscripts rather indicate what things have been differentiated with respect to. And now if you look at this, first of all, it vanishes, because if I put H1, wait, on the solution set, because if I put H1, H2 and H3 0, the last column is all 0. But it's also the case that if I differentiate, say, with respect to x, then I can see that the various columns cancel and so on. Similarly with the differentiate with respect to y. So by inspection, it's easy to see in this case, first of all, that it vanishes on the solution set. Secondly, that secondly, it doesn't depend on x and y, and so it gives you an equation for z over u, and that equation you can check is a sextic. So you have an order 6 equation for z over u, and once you've determined z over u, then everything else is determined in terms of that. So the different solutions that you get here will give you the different points which are the solutions of the scattering equation. And in some sense, therefore the coefficients in this sextic are the things which are carrying the information about the original equations, and actually rather than work out these roots, you want to express the amplitude in terms of as a rational function of the whatever's in the numerator together with these coefficients of this sextic. And then for general n, we'll have something of order n minus 3 factorial, but of course that quickly gets tough. But there is a way of not just guessing it, which is sort of how we got to that, which is due, I think, to Sylvester. And that is the following: that you take the 3 equations you have. So you have an equation which is you have an equation which is linear in x, y, and z. You have one which is quadratic and one which is cubic, but none of them involve squares. Now forget the fact that none of them hold squares, but let's just assume that we have 3 things which sorry, I said the wrong thing. You remember none of them involve squares, but what you don't take advantage of the fact that one of them is linear and one of them is quadratic and one of them is cubic. They all might be cubic from the point of view of this analysis. It doesn't matter. So you then take the 3 equations you have, which read that this should vanish, where C and D and B and A can contain the other variables, but since it's square free in x and y, you can't have anything which is more complicated than this. And then you also consider the same equations multiplied by x, and you get another set of equations, and these 6 equations must vanish. Now these 6 equations now involve, if you treat these as just for the moment as different variables, they involve 6 variables, and so it must be that if you delete these things, their determinant must vanish. So you look at the determinant of that, and that determinant actually is equivalent to, after a bit of easy manipulation, to something which is what we wrote down before here. So this is a standard technique of Sylvester's for solving equations like this, developed later by Cayley, and of course the complication comes when you have more complicated examples of what you're dealing with. So for the purposes of writing down the next stage, it's not really necessary to write down these 3 equations individually and those 3 equations individually. So I'll write them down, I'll condense them into a 3-vector H and 3-vector HY and so on. So here, so in that notation, I can write this 6 by 6 determinant as a 2 by 6. So next time, so for n equals 7, we want to get essentially something of order 24, and we want 24 equations. And it turns out the 24 equations will work. I've written down here. So for each component of H, and you know H is now H1, H2, H3, H4. you multiply it by x and y, or by xy, or by x squared, or by x squared y. And after you've done that, you've got 24 equations. And the variables that those equations involve are exactly 24 variables, if you look them out. And so you can write down the condition that that's consistent, and you get this determinant here. So that determinant, you can check, gives you an equation of order 24 in the other variables, say u and t, and so it will determine the 24 points that you get in that case. But again, as I say, I'm not really advocating that one should approach this from the point of view of solving these things, though it's not too difficult to do that with the aid of a computer. But it gives you a way of actually getting a hand on the equation, showing that it's non-singular. Because one thing that could happen in this procedure is I get nothing equal to nothing. You can check that doesn't happen. That's very important. You can check, and it actually took us a bit of effort to do that the whole thing didn't collapse to 0 equals 0. So in general, you want n minus 3 factorial equations. You multiply them by suitable powers of the z's, which I've called x here, and you have somewhat more variables, and the whole thing works in general. So for example, for n equals 8, this number is now 120. You multiply by powers of this time x, y, and z, where z could be z or 1, y could be y squared y or 1, and x could be x cubed, x squared, x or 1. And then you get equations relating 120 quantities, where here, for example, x can be anything from 1, this factor here could be anything from 1 to x to the 4th, and so on along. And again, as I say, you get something which you write down if you want. I won't go through this, what that determinant is, and see how it works explicitly. Now, I think I can either discuss four-dimensional space-time, or I could discuss Möbius invariance some more. What should I do? 4D? Okay. So, so one feature of this, if we're thinking about four-dimensional space, is that we know in four-dimensional space the important thing in understanding the solutions at the tree level or above is to look at the helicities. And of course, when we're talking about gauge theories, and of course I've stressed that I'm interested in scalar theories, but still somehow those things ought to come out, and you can sort of see how those things are to some extent in four dimensions embedded, but not as far as I can see in high dimension. So how does the idea of solutions having a particular helicity attached to them come out? So if we're looking at the contributions to tree amplitudes in gauge theory, for example, then the total number of solutions, the total number of contributions we get are going to be this n minus 3 factorial, but they're going to split into things in which there are different divisions between the positive and the negative helicity. And that's actually encoded in the particular solutions that you look at. So if we have a solution to the equations, then given by some set of ZAs, then we can form this thing which whose square identically vanishes. So P here, which is P, this thing here doesn't vanish, but its square vanishes. That vanishes identically for all values of Z. Now, if we just, for sake of, again, clear out the fractions, then we've got this thing P mu here, which is a polynomial function of Z, whose square is 0. And so actually if we write this in a matrix form, then the determinant of this matrix is 0. And since the determinant of the matrix is 0, it must have 0 eigenvectors, both sort of on the left and on the right. So the fact that the determinant equals 0 means that this times this is that times that. That's just another way of writing out that p squared is 0 in 4 dimensions. But then we can divide this by p1 plus ip2 and p0 plus p3. So this just means adding the relevant indices. And we can then take this thing, which typically will not be neither of these will be typically in their lowest form. So in other words, these two components may have common factors. Typically, will have common factors actually. And so if we take out the common factors, then write it in its lowest form, then it will have some form here. So this pi1 over pi2 is this fraction, which is a rational function of two polynomials written in its lowest form. And then it follows that for each of these two things, we can write here p is something times p2, and this is the same thing times p1, and so on. And when you do that, you get this familiar twistor type expression for what p is. Now, so p itself is a polynomial of degree m minus 2. You might think it was m minus 1, but momentum conservation knocks out the highest power. And so the other two quantities you have introduced now, these twistor quantities, must have degrees which actually add up in the appropriate way to m minus 2. And they are their degrees are determined, sort of, if you like, topologically. They're the number of times this thing is going around the origin. As you say, Z goes around the origin, the number of times this thing loops. So it's a sort of n is a topological attribute of the solution, and is the number of negative helicities in the gauge theory context. And you can from that then deduce these equations, and I've forgotten whose paper this first occurred in, but earlier than all this other stuff, Witten or somebody. Whose was it? Witten. Which are the sort of twistor versions, if you like, of the scattering equations. And all of this discussion is particular to 4 dimensions. Okay, so I think that is where I'll stop.
Can you just go back one transparency?
One more?
Well, to the bottom of that one.
More?
There was one bit where you said that the number of solutions... Sorry, my question was the number of solutions to the sort of 4-dimensional refinement of the scattering equations. I believe that RSV conjectured it was equal to this Eulerian number. That's now proved.
No. Not by us.
Right.
No, sorry, I should have made that clear. That's an observation. Yeah. It has to be a set of numbers which add up to the right number, but we don't know what they are, except we do know what they are.
Sure.
Of course, the other strange thing about this is that you can somehow attribute you could say, well, which k's is it have to have the positive and which have to have the negative velocities, and that's at your freedom. So in other
You can
words,
write down a version where you specify.
sorry?
You can write down a version where you specify which are the plus and which are the minuses.
But if I'm given a set of z's here, and then I can then attribute whichever k's I like to positive and negative velocity.
Well, sorry, yeah, maybe I'll...
Yeah. Okay.
We'll
we can discuss what we mean
Yeah, because I'm not quite sure.
afterwards.
Given that these, in 4 dimensions, do you see in the scalar theory any role for these different subsets?
No, I mean this is one place in which, if you like, there is a sort of, in 4 dimensions, a hidden, some hidden vestige of spin, it seems, which was perplexing. Which is why we sort of looked for it. Actually, Son was pointed us in the direction of understanding that a bit better. But let me just I'll just say 2 or 3 sentences about what I didn't say in the last section. I won't do it. But one of the questions you can ask is, could you write down other equations like this? So, in other words, you could look at this equation here. You could rub out k squared, and you could put, say, phi as some coefficient. And you could say you have a set of equations like this. What are the possibilities? So there was some discussion this morning about what other things could you do like this. And so you want those equations to be Möbius invariant. So what that then means is you can sort this out by group theory. So you look at the set of the space spanned by the ZS's. That's a space of dimension 2 to the n, because each Z is either there or it isn't. And under the action of the Möbius group, it moves into itself. It's a product. It's the tensor product of 2-dimensional representations of the Möbius group. So you can think of the Möbius group acting on each Z independently, and you take and for each Z you've just got 1 or Z, and so that's a 2-dimensional representation. You take the product, and so the product then corresponds to various spins. This is Möbius spins. If you take so these Möbius spins go from, there's one representation which sort of starts from 1 and goes all the way down, which has a Möbius spin n over 2. And then there's one that has, so there's one of those, and then there's n minus 1 subspaces which have dimension n over 2 minus, have spin n minus 2 over 1. So the dimension of this is twice this plus 1. It's 2l plus 1. So this is dimension n plus 1. It goes from 1 up to the product of all the z's. This, and it consists actually of all the symmetric functions. This has dimension n, this has dimension n minus 1. And then you have this one, which is one we're interested in, which has dimension n minus 3, twice that plus 1. With these, there are too many equations to determine a variety. In other words, if you look at the set which it satisfies, it's null. I mean, it's empty. With this, you have just the right number. And there's a certain number of these. I've forgotten what it is, but it's some quadratic in n. And every one of them corresponds to a configuration of massless particles. So there's exactly the right number or the dimension of representations there to correspond to the possible configurations of massless particles in an arbitrary dimension. Then the solution of those equations, because there are n minus 3 of them, are points projectively. When you then look at the next slot down, you've got more representations typically, and they won't determine points. They'll determine some variety of non-zero dimension. So you can look at those equations if you like, but then you'd have to not sum over the solutions. You'd have to integrate. But they do correspond to equations which are just like the ones that we've been talking about. That is, you can write them in terms of some tensor over z minus a, z minus b, z minus c, and so on. So they have a very similar structure. Mathematically, much of the analysis would be the same, but now whether they have any physical relevance, I have no idea. Now, another thing you could do is that this is a particular way of realizing the action of the Möbius group. It's realizing it so that you never get beyond things which are square free. But you could. There are other ways of on multinomials of realizing the action of the Möbius group, and then you would get different sorts of equations. Those equations almost certainly do come in when you study when you look at, say, higher order poles in these things. But there's a whole range of different things that you can do there. But I guess the point I was trying to allude to was that the equations we have a special status, and they're all the ones there are of that status. So there's a mathematical point of view from which they are natural. Thank you.
Is there any more questions? Hi, Peter.